8.4, vector and parametric equations of a plane. So we're going to shift focus from lines, so vector and parametric equation of lines, to actual planes, okay? And just a recall of what a plane is, planes are flat surfaces that it can extend infinitely far in all directions. Planes are usually represented by parallelograms. As you can see below, there's 4 on this page, okay? And the understanding is that when a plane is represented by a parallelogram, that parallelogram extends in all directions, okay? So even though it's a parallelogram, it actually goes up more and more here, and then to the right as well, and then the bottom comes down and the left comes, okay? So it's actually going infinitely far in all directions, okay? So planes are denoted with the Greek letter pi. So you might see pi and then colon, and then the equation of a plane. Okay, and in real life, when we think about planes, planes can be represented by like the top of a desk or a wall, okay? And of course, walls, you have like the floor, one wall, and then of course the other wall, and those all meet. And this is actually going to be a very, very important visual where they meet here. So if you take a look in your room right now at the corner where they meet, the 2 walls and the floor, that's going to come back. You're going to see that, okay? Or ice surface on a hockey rink, for example, okay? Just some examples in real life. So planes can be determined if we're given any of the following. So if we're given a line and a point that's not on the line, okay? So a line and just a random point, we can determine the equation of a plane. Okay, 3 non-collinear points. You're not in order, this should be B, that's fine. 2 intersecting lines. Okay, so 2 lines here and then intersecting, and of course, that means that we have 2 lines and a point. And then 2 parallel and non-coincident lines. Okay, so parallel and non-coincident, so that they can't actually lie on top of one another. Non-coincident means that they're distinct. In other words, like if we go back to grade 9, they have a different y-intercept. Okay, so let's do an example of each one of these and see how we can determine the vector and parametric equations of a plane. So a lot of what we see here is going to look very familiar, and it's going to look familiar from the equations of a line. So in r cubed, so if one of our points are not, the vector r naught is x, y, z, is determined by a point on the plane. So this x, y, z is just a point, okay? Then vector a and vector b are direction vectors. Then the vector equation is going to be in this form. Okay, so if we read this together, vector on here, okay, the equation of the plane is going to be the point plus a parameter and a direction vector and another parameter and another direction vector. Okay, and the parameters s and t are elements of the real number system. Okay, to see that just expanded still in the vector form of an equation of a plane, the point ABC, parameter times direction vector, parameter times direction vector. Okay, likewise for parametric forms, what we want to do is we want to break up the x, y, and z components. Okay, the point x, y, z, direction vector number 1, so a1, a2, a3, oops, 3a there, and then b1, b2, b3. And just note that there are no symmetric equations of a plane. Okay, we must have 2 unique direction vectors, or else what it's saying is like, we're just saying like, oh, keep going in the same direction. So we actually need 2 unique direction vectors in order to show 2 different ways that the plane extends, right? And we're going to have 2 parameters for that, for the equation of a plane. Okay, and then please note, replacing the parameters in a vector and parametric equations of a plane with numbers generates points on that plane. Okay, so just similar to a line, when we replace like the parameter t with a number, we would get more points on the line. This time, if we replace s, the parameters s and t, we're going to put points on that plane. Okay, and there's an infinite number of points that lie on a plane, just like there's an infinite number of points that lie on a line. Okay, so example 1a, determine a vector equation and the corresponding parametric equations for a plane that contains these 3 points. Okay, so just to recall the equation of a plane, we need to have a point. So let's just pick point A, because why even bother thinking about it? Just pick the first point you see. Okay, then what we're going to have is we're going to have plus the parameter s and a direction vector, and then plus the parameter t and a direction vector. So what we need to do is we need to find 2 direction vectors. So let's find direction vector AB. Okay, so -1 minus -1, comma, 1 minus 3, comma, 0 minus 8. So -1 plus 1 basically is 0, -2, -8. So we can go ahead and sub that in right here. Okay, 0, -2, -8. And just be aware that if you find AB or if you find BA, again, it's a multiple of -1. So if you found, just for an example, if you found BA, vector BA, you're actually going to get 0, 2, and 8. However, because these are equivalent, we cannot use both of them. We have to find a unique one. So let's go BC. Okay, so let's go 4 minus -1, comma, 1 minus 1, 1 minus 0. 1 minus 1, 1 minus 0. Okay, so we get 5, 0, 1. Okay, and then that's going to be our second direction vector, and that's it, 5, 0, 1. So here's the vector equation of the plane that contains these 3 points. And now all we have to do is simply break it down into the x, y, and z components. So let's see every single number that corresponds with x. -1 plus 0s plus 5t. Okay, if you want to leave out the 0s, you can. Now the y's. 3 minus 2s plus 0t. Okay, again, you can leave out the 0t. And then the z. 8 minus 8s plus t. Okay, and there are our corresponding parametric equations. Now, part B asks, I'm going to change the color. Part B asks, do either of these points lie on this plane? So let's put this on the next page. Okay, so all I've done is clear the board, and I just wrote the parametric equations. Just please note that for like the x parametric equation, I didn't write in the 0s, and for the parametric equation for the y, I didn't write in plus 0t. Okay, so let's test if p lies on the line. So what we want to do is, if p lies on the line, 14, 1, 3, what's going to happen is that all of these parameters are going to be the same. So this is actually quite a nice, these are nice parameters because we only have a t as a parameter in x, and we only have an s as a parameter in y. So this is going to be very easy to solve for. So let's go ahead and sub in 14 for x. Okay, so let's bring over that -1. I get 14 plus 1 equals 5t. So it's 15 equals 5t, and then obviously cancel those out, t equals 3. So we get t equals 3 as the parameter. Now, let's do the same thing for y. Let's sub in 1 for y. And I'm going to start skipping a couple steps. Okay, bring the 3 over, 1 minus 3, and then we're going to divide out that -2. So for the parameter s, I get, that'd be -2 over -2, s equals 1. So in order for the point 14, 1, 3 to lie on this line, if we sub in the parameters 3 and 1 into z, we should be able to pop out the number. we should be able to get the number 3. So let's go ahead and try that. So if we took z as 8 minus 8s plus t, let's go 8 minus 8 cancels, so I get z equals 3. Okay, go back up here, z does equal 3, therefore p lies on the line. Sorry, p lies on the plane. Okay, so likewise, we can do the same thing, test if q lies on the plane. Okay, you should be able to go ahead and try that. So first of all, p and q, 14, 1, 3. Well, 14, 1, we already have the parameters for that. We already subbed that in. We would get the exact same parameters, of course. Now let's test 5. So pretty much what this question is allowing us to do is it's allowing us to see when a point lies on the plane and how it works and how z equals 3, which matches with this. Okay, and it's going to show us when it doesn't work. Okay, so 8 minus 8 cancel out. Oh, well, z equals, I mean, if we isolate for z, z equals 3. Okay, but we have a z as in 5. 5 does not equal 3, therefore q does not lie on the plane. And that's how we find an equation of a plane when we're given 3 points. Okay, example 2. A plane pi has the equation here, the vector equation here, where s and t, the parameters, are elements of the real number system as its equation. Okay, so this is the equation of our plane. Determine the point of intersection between pi, which is the plane, and the z-axis. Okay, so first what I'm going to do is I'm just going to note that the intersection of the z-axis is going to be 0, 0, and then some letter. We can either call it A, B, C, so we can call it C, or we can call it X, Y, Z. We could have called that Z. Okay, so first what we're going to do is we're going to write the parametric equations out. Okay, this time I'm going to show you something a little bit different. I'm going to go down. So 6, negative 2, negative 3. So 6, negative 2, negative 3. Okay, now plus 1s, 3s, 0s, plus 1s, plus 3s, and I'm just going to leave out the s here. Okay, plus 2t plus 2t minus t. Okay, so there are our parametric equations. Okay, so from here, what we want to do is we want to plug in what we know. Okay, so we know that x equals 0 and y equals 0. So let's go ahead. So I'm going to change colors. Deep purple. Okay, so let's write the x equation with a 0 in it. 6 plus s plus 2t. Now let's write the y equation with a 0 in it. 0 equals negative 2 plus s. Oh, you know what? I'm going to stack these. I'm going to show you why in 1 second. 0 equals negative 2 plus 3s plus 2t. Okay, so now we have 2 equations, 2 unknowns, brings us back to grade 10. What we want to do is either substitution or elimination. Okay, so just as like a quick little recall, we have 2t and 2t. That means that I'm going to do equation 1 minus equation 2. 0 minus 0 equals 0. 6 minus negative 2 equals 8. S minus 3s, I get negative 2s. And then those ones, of course, cancel. Now, from this point, I can just rearrange. Negative 8 equals negative 2s. Divide both sides by negative 2. I get s equals 4. Okay. From there, we have s, and we want to sub it back into either one of the originals. So equation 1 or equation 2. I'll just take equation 1. That's fine with me. Okay, 0 equals 6 plus 4, which is our s value, plus 2t. Okay, and now let's just solve. So 6 plus 4 is 10, and let's bring that over. Negative 10 equals 2t. Divide out that 2, we get t equals negative 5. Okay, so we have the two parameters that s and t, so s equals 4, t equals negative 5, that we need in order to find the intersection of this plane with the z-axis. So our z component, z equals negative 3 minus t. Oh, we actually didn't even need s, but we did need s in order to solve for t there because it was easier to find, so that's fine. Z equals negative 3 minus, and then that's like that double negative, okay? So it's like negative 3 plus 5. I get z equals, what is that, 2. Okay, so the point of intersection is, I'm going to do this in another color. Okay, therefore, point of intersection between pi and the z-axis is 0, 0, 2. Okay, example 3. So determine the vector and parametric equations of the plane containing this point, P, and then this line. Okay, so what we have here is we have some plane, and it contains a line and a point. Okay, so first of all, because it contains this line, it actually shares this direction vector. Okay, so let's start our equation. Let's see what we have so far. So we do have a point. It contains the point P. So let's actually just write the point P, 1, negative 5, 9. Okay, and then we're going to write plus S. And then since we have a line that lies on this plane, we're going to have the same direction vector. It makes sense that the plane also has the direction vector, negative 1, 1, 0. Now, what we're missing is this second direction vector. And just remember, S and T are elements of the real number system. Okay, so how do we find a direction vector? Well, we know that we have point P, 1, negative 5, 9. Okay, but we also know that our plane includes the point 1, 1, 1. Okay, let's just call that Q. Because our plane contains this line, our plane by default contains this point. So let's actually find direction vector PQ. So let's go Q minus P. 1 minus 1 is 0. 1 minus negative 5 is 6. 1 minus negative 5 is 6. And then 1 minus 9 is just a negative 8. So this is our new direction vector PQ, and we can just sub that in for our second direction vector for the plane. And that's it. So that is the vector equation for the plane. Now, let's just break that down into parametric. So X, Y, Z. The point 1, negative 5, 9. Okay, parameter S minus S plus S, and then 0S, so we'll just leave that out of there. 0T, we're going to leave that out of there. So that one's done. Plus 6T minus 8T. And there are our parametric equations for the plane containing point P and line L.